In this video, we're going to talk about the linear approximation table of an S-box. Here's a list of our topics for this talk. We're first just going to introduce what we're going to define and a little bit of motivation of why we'd want to study that. And then we'll talk about the field of two elements, sequences of bits, the dot product, the definition of what an S-box is, and we'll talk about linear equations associated to an S-box. We'll talk about bias and probability and linear equations and bias. And then we'll finally be able to define the LAT of an S-box. And then we'll talk about the properties of the LAT and some things about the complexity and calculating it. And then we'll code it. We'll talk about how we can print it to a text file. And then we'll calculate the LAT of the S-boxes in Haze tutorial. And we'll calculate the LAT of the Rijndael S-box as well to end the video. So in this talk, we're going to define the linear approximation table L of any S-box. And we abbreviate linear approximation table by LAT. So suppose we're given an S-box S, and let's say it takes n-bit sequences to m-bit sequences. The LAT L of S is going to be a table, or if you want, you can think of it as a matrix. It'll have 2 to the n rows and 2 to the m columns. The entries of the LAT will consist all of integers, and this includes positive and negative and 0. So a LAT can have negative integer entries. Now, some motivation of why we would want to study this is that it's related to linear cryptanalysis. If you have a block cipher that you want to attack, you would first look at the S-boxes involved in the design of that block cipher. And if you wanted to attack that block cipher with linear cryptanalysis, you would calculate the LAT of the S-boxes involved in the design of that block cipher. And how does the LAT reveal a potential vulnerability in the S-box? Is if it has a large entry in its LAT. It either has a large positive or large negative integer contained in the table, and that's a sign that there might be an attack available through linear cryptanalysis. We won't talk about linear cryptanalysis in this video. We will in a future video, but here we're just talking about the LAT. To start it off, let's just say we define F2 to be the field of two elements, so just 0 and 1. And we interpret, of course, F2 as just a set of bits, 0 and 1. And on F2, we have two operations, which we can call addition and multiplication. And under those two operations, F2 becomes a field. The addition operation on F2 is just the logical operator XOR. And the multiplication operation on F2 is the logical operator AND. And usually when we won't write the AND usually to abbreviate X and Y, we'll just write XY. So when we write X and Y beside each other, it means multiplication, and the multiplication is the AND operator. Okay, and now we'll take sequences of these bits. We'll imagine we fix a positive integer n, and then we think of all possible bit sequences of length n. And we can consider those as maybe tuples, x1 up to xn. And the set of all those is f2n. Now f2n will have 2 to the n elements since we have n independent coordinates here. And each coordinate can take on 2 different values. We have 2 to the n possibilities. And if we think of the integers in the set from 0 to 2 to the n minus 1 as their base 2 bit expansions, that gives us an identification between f2n and the set of integers between 0 to 2 to the n minus 1. So those sets are equivalent in some sense. Now we can define a dot product operation on f2n. In fact, the dot product is really a map from f2n cross f2n to f2. So in other words, we take two sequences of bits, each of length n, and then we produce an element of f2, which we denote x dot y, And it's just the sum of their products. So you multiply all the xi, yi with the AND operator, and then you XOR them all together, and you get x dot y. So just notice that x dot y is an element of F2. It's not an element of Fn, right? Now, in the upcoming parts of the video, we're going to encounter an expression that we're going to see all the time, and it's kind of the form alpha dot x plus beta dot y, where alpha and x are in F2n and beta and y are in F2m. So let's just spend just a second to look at this expression and make sure we understand it. When we write alpha dot x, since alpha and x are both sequences of n bits, we can define their dot product, and we get alpha dot x, which is an element of F2. And beta and y are m-bit sequences, so we can calculate their dot product. That's given by beta dot y, and that's in F2 as well. And then we take the two elements of F2, alpha dot x and beta dot y, and then we XOR them. And in the end, we get an element of F2. So it's pretty obvious. I just wanted to run through that because this will be a very important expression that we'll see in a second. Let's just review the definition of an S-box. If we have two positive integers n and m, any function from F2n to F2m will be called an S-box. So it's just really any function which takes n-bit sequences to m-bit sequences. And we call n as the number of input bits and m as the number of output bits. Now let's say we're given an S-box, S from F2n to F2m, and we're going to talk about the linear equations associated to an S-box. And the way we construct these equations is like this. We take two fixed vectors, alpha and beta. Alpha is in F2n and beta is in F2m. And we're interested in solutions, x, which come from F2n, of the following equation, which is alpha dot x plus beta dot s of x equal to 0. There's that expression we just looked at. We call alpha and beta the masks of this equation. Alpha is the input mask and beta is the output mask. Let's just take a little bit closer look at this equation. I'm not really a fan of this style of notation, but why don't we call x1 up to xn our input variables? Those are all in F2. And then we take those n input bits, we put it into S, and then we get m output bits, and we call those y1 up to ym. The reason I don't like this notation very much is that the yi aren't really free variables, but they're determined by the choice of the xi, right? Once you fix x1 up to xn, then you get the value of yi for each I. So yi are dependent on the xi. So just make a note of that. Now, the reason we call this a linear equation is because alpha dot x plus beta dot sx equal to 0 can just be written as the sum of alpha 1 x1 up to alpha n xn plus beta 1 y1 up to beta m ym equals 0. And that's the typical format of a linear equation, right? Just remember all the alpha I xi and the beta I yi, they have an and between them. They're being multiplied. So this is a linear equation in the input variables xi and the output variables yi. And that just kind of justifies the use of the term linear when we talk about that equation as being a linear equation. Now here's where we start to make a few definitions and notation to start studying this thing. Why don't we take any S-box S from F2n to F2m, and let's fix some masks, alpha and beta. Alpha is n bits and beta is m bits. And then we're going to define, we need a notation for the set of solutions. So let's just call that sigma alpha beta. So capital sigma alpha beta is just a set of all x in F2n, which satisfies that main equation that we're talking about. Alpha dot x plus beta dot s of x equal to 0. And so sigma alpha beta is a subset of F2n. It's the set of solutions to that equation for some fixed alpha and beta. And let's also define the cardinality of that subset. So let's define E alpha sub beta to be the cardinality of the set of solutions. You know, since sigma alpha beta is a subset of F2n, then the cardinality E alpha beta has to be bounded between 0 and 2 to the n. Just remember the cardinality of f2n is 2 to the n. So the cardinalities of our solution sets of that main equation will always be, obviously, between 0 and 2 to the n. That's just an obvious rough bound. So we've defined sigma alpha beta as a set of solutions and E alpha beta as the number of solutions. All right, so let's just take a little pause and talk about probability for a second. Let's say you have a probability P of some event. Then what does that mean? P is a real number. It's between 0 and 1. It could be 0, it could be 1. And P equals 0 means the event is impossible. P equals 1 means the event is guaranteed to happen. Now, from a given probability P, we can define an associated quantity, an equivalent quantity called the bias. And we're going to usually denote that by epsilon. And to define the bias epsilon from the probability P, it's easy. You just do P minus a half. So the bias epsilon is equal to the probability P minus a half. So since the probability lives between 0 and 1, and the bias is just 1/2 smaller than the probability, that means the bias is a real number between negative 1/2 and 1/2. So notice the bias can be a negative value. That's possible. Now, conversely, obviously, if we have a bias given to us epsilon and you're curious what the associated probability is, to get that, all you do is you take your bias epsilon and you add a half, and then you're back at the probability. So we can go between the bias and the probability. Now, just notice P equals 0 and P equals 1 are the edge cases of a probability value. And then the edge cases of the bias value is negative 1/2 and 1/2. And just notice also a probability of a half has a bias of 0, right? 1/2 minus 1/2 is 0. So for example, a toss of a fair coin, it can come out either way, and that has a bias of 0. So a fair event has a bias of 0. We can talk about the bias of a linear equation being true or not. And let's first just talk about the probability of a linear equation being true. So let's fix our masks, alpha and beta, and then let's look at our main equation, alpha dot x plus beta dot s of x equal to 0. The number of solutions to that, recall, we've defined as E alpha beta. And it's just, of course, the cardinality of the solution set, sigma alpha beta. So what's the probability that an element of f2n satisfies our equation? Well, it's just the cardinality of the subset of solutions divided by the cardinality of the entire set, which is E alpha beta over 2 to the n. So we define P alpha beta, that's another quantity we define, to be the E alpha beta over 2 to the n. And that's the probability that a random element x in f2n satisfies our linear equation associated to alpha and beta. Just remember, for any alpha and beta, we get an equation, right? And that equation will have E alpha beta number of solutions. And just like with all probabilities, P alpha beta, it's going to live between 0 and 1. We're more interested in the bias than the probability. So the bias of that equation, therefore, epsilon alpha beta, which is another quantity we define, it's P alpha beta minus a half. Just take a half from the probability, and we'll have the bias of our linear equation holding, okay? Now, why don't we just substitute? We know that P alpha beta is E alpha beta over 2 to the n, so why don't we substitute that in our equation for the bias? So epsilon is P minus a half, which is E over 2 to the n minus a half. And then you get a common denominator, and you see it's E minus 2 to the n minus 1 over 2 to the n. I'm saying E, but I really should say E alpha beta. So the bias can be expressed as a fraction. The denominator is 2 to the n, and the numerator is E alpha beta minus 2 to the n minus 1. And we're going to give that a special notation. We're going to call that E alpha beta prime. And that's what we're going to call the bias integer. And that's, in fact, the entry of the LAT. Those bias integers, those numerators of the bias value, namely E minus 2 to the n minus 1, those are the entries of the LAT. Those are the values of interest for us. So E prime alpha beta is E alpha beta minus 2 to the n minus 1. That's an important definition. Those are the entries of the LAT. Like, recall that E alpha beta is between 0 and 2 to the n. If we subtract 2 to the n minus 1 from each of the sides of this inequality, we get 0 minus 2 to the n minus 1 is less than or equal to E alpha beta minus 2 to the n minus 1 is less than or equal to 2 to the n minus 2 to the n minus 1. And just notice that, 2 to the n minus 2 to the n minus 1 is in fact 2 to the n minus 1. I'll leave that for you to prove. For example, if n is equal to 4, that just says 16 minus 8 is 8. And now if we put that in our inequality, we find the following bound for the bias integers. The E prime alpha beta is bounded between negative 2 to the n minus 1 and 2 to the n minus 1. And that means the entries of our LAT are going to be in that range. Now, by definition, how do we get the bias from the bias integer? Well, just put it over 2 to the n, right? So if you know the bias integer, E prime, to get the corresponding bias epsilon, just put it over 2 to the n. Now we're finally ready to define the LAT of an S-box. So let's take S to be an S-box with n input bits and m output bits. The linear approximation table of S, abbreviated LAT, it's a table. It has 2 to the n rows and 2 to the n columns, so it's a little bit large. All the entries will be integers, positive, negative, or 0. We usually denote it by script L. The rows are going to be indexed by the elements alpha and F2n. Rows are horizontal, remember? The columns, which are vertical, are indexed by the elements beta and F2m. The entry at row index alpha and column index beta, it's just given by the bias integer E prime alpha beta. So script L is a table, and the entries in there are E prime alpha beta. And so roughly speaking, the LAT is just a table of all the possible bias integers. For any LAT, the first column is always the same. It's always going to have a 2 to the n minus 1 in the upper left corner and then zeros below for the first column. So I just filled those in already on this one. But the other numbers past the first column will be mysteries until we calculate them using our code that we'll write a little bit later. So that's how we define the LAT of an S-box. Now this section's a little bit technical. You might want to skip it on the first viewing, but all I'm going to prove here is, notice at the bottom, it says the value in the upper left corner is 2 to the n minus 1. That's the first thing we'll talk about. And then we'll do a little lemma, maybe not too important on the first viewing. And then we're going to prove what I just mentioned, that on the first column, everything is zeros below the 2 to the n minus 1, okay? And then we'll talk about the LAT of the inverse is just a transpose of the LAT of the original. And then we'll prove an important little result here, that when n is bigger than 1 and the S-box is bijective, all the entries of the LAT are even integers. Well, when we calculate it, we're going to see that all the time we get these even integers. And here's a proof that that's always the case. It's not that important on the first viewing. You may want to skip it and just get back to the main video here, which is less technical. We've already proven that the entries of the LAT, E prime, alpha beta, they lie between negative 2 to the n minus 1 and 2 to the n minus 1. And that's the topmost inequality I have here in the box on the right-hand side. So let's look at the case alpha equals 0 and beta equals 0. That corresponds to the entry in the upper left corner of the LAT. When alpha and beta are both 0, our main equation, alpha dot x plus beta dot x, just degenerates into 0 equals 0. And that means every element x in F2n is the solution to that equation. So our solution set, sigma 0, 0, is in fact all of F2n. And therefore the cardinality of our solution set, E0, 0, is 2 to the n, as big as it can be. And how do we get our bias integer? Well, E prime 0, 0, by definition, is E0, 0 minus 2 to the n minus 1. So we encounter, again, that quantity 2 to the n minus 2 to the n minus 1, which is 2 to the n minus 1. So we've just proven that for any lat, the value in the upper left corner is always 2 to the n minus 1. And we record these two little properties in our box on the side here. E00, the number of solutions is 2 to the n, but E00 isn't the number in the lat. We need the bias integer. And to get the bias integer, we subtract 2 to the n minus 1 from 2 to the n. And that gives us E prime 00 is 2 to the n minus 1. And that shows us that we always have 2 to the n minus 1 in the upper left corner. Now, this is a little bit of a technical lemma. We just need to prove this to get the results later on that we need. If we take an element of f2n, and it's not going to be 0, and we're also assuming that n is not 1 here, so n is bigger than 1. We're going to define a subset of f2n called w, and it's a set of all elements whose dot product with alpha is 0. So w is the set of all x in f2n such that alpha dot x is 0. And we would like to prove that the cardinality of w is 2 to the n minus 1. Okay. Now, since alpha is not 0, we can find an index I0 such that alpha sub I0 is not 0. In other words, it's equal to 1, right? It's either equal to 0 or 1. If it's not 0, it must be 1. Now, that index really could appear anywhere, but just for the sake of our notation that will be a little bit easier, we can really just assume that the index is at index 1. So we can assume I0 is 1. And that means that alpha 1 is non-zero, so alpha 1 is equal to 1. The argument we're going to give could apply to any index. It'll be the same. So let's just, for ease of notation, assume that alpha 1 is the place where it's not 0. So alpha 1 is 1. And that means we can separate it a little bit. We can write alpha equal to 1, the first coordinate, comma alpha prime, where alpha prime now has n minus 1 coordinates. Alpha prime is in f2 n minus 1. Now we're going to define a map phi from f2 n minus 1 to w. We'll take an element x in f2 n minus 1 and we'll map it to, well, the first coordinate is going to be alpha prime dot x. That's an element of f2. And then the second coordinate is just x. So notice it's an identity on the second coordinate there. The second coordinate x there is kind of like a free variable. It ranges over f2 n minus 1. And then the first coordinate, alpha dot x, which is an element of f2, is determined from the choice of x. And we can easily check it's well defined because alpha dot phi of x is just alpha dot that vector we defined. And if you think about that for a second, it just turns out to be alpha dot x plus alpha dot x. And when you add two elements that are the same, you always get 0, right? In f2, z plus z is always 0. Now, it's easy to see that phi is a bijection. Because the last coordinate of phi of x is x, it follows right away that it's a one-to-one map. And if you think about it, it's also onto. So phi is establishing a bijection between our set w and f2 n minus 1. And now we're done, right? Because we know that since it's a bijection, the cardinalities are the same. And the cardinality of f2 n minus 1 is 2 to the n minus 1. So we've proven the cardinality of w is 2 to the n minus 1. Now, on this little slide, our goal is just to prove that the entries of the first column are all 0, except for that first one, which is 2 to the n minus 1. So let's take, that first column corresponds to beta equals 0, right? And if we're not at the first entry on the first column, then alpha would be non-zero. So we imagine that alpha is not 0 and beta is 0. Our main equation, alpha dot x plus beta dot s of x being 0, when beta equals 0, it actually just becomes much simpler. It just becomes alpha dot x equal to 0 now. And that's exactly the expression that we had in that lemma, right? Remember, w is the set of all x, which make that true. And we now know that the number of those x is going to be 2 to the n minus 1 by that lemma, right? And that means the number of solutions, E alpha 0 is 2 to the n minus 1. We write that down in our box on the right-hand side there. And once we know E alpha 0, we can easily find E prime alpha 0. Just do E alpha 0 minus 2 to the n minus 1. And we end up with 2 to the n minus 1 minus 2 to the n minus 1, which is 0. So we've just proven that the first column of any LAT, we understand it. The first entry is 2 to the n minus 1, and then everything below it is zeros. We write that in our box on the right-hand side to summarize what we're doing here. And the case, the case beta equals 0 is not even of any interest in applications, because when beta is 0, beta dot s of x just disappears. And that means the beta equals 0 case doesn't even involve the S-box S. So we just prove this because it's true, but it's not of really any use. Now, usually with an S-box, it's going to be a bijection, right? So that means n is going to be equal to m. So if we have an S-box from f2n to f2n, which is a bijection, then the inverse is also going to go from f2n to f2n. How about we just take an element x in f2n and define y to be s of x, which is also in f2n. Then just by definition, the S-box S inverse is going to map y to x. So S inverse of y is equal to x. Now, how does our main equation change? Well, it's alpha dot x plus beta dot s of x equals 0. Alpha dot x, since x is S inverse y, becomes alpha dot S inverse y. Beta dot s of x becomes beta dot y. And so it's equivalent to beta dot y plus alpha dot s inverse of y. Notice the alpha and beta, they changed positions kind of. But other than that, it's the same equation except for S inverse. So we've just proven a symmetry between the solution numbers between E S alpha beta and E S inverse beta alpha. We can express this with kind of matrix notation like transpose. Remember the transpose of a matrix? You just interchange the rows and columns. So we've actually just shown that the LAT of S inverse is the transpose of the LAT of S. So if you know the LAT of S, you can easily generate the LAT of the inverse of S. We've already seen that the first column is all zeros except for that first entry, 2 to the n minus 1. From this result, we see that the first row is also all zeros except for that first entry, 2 to the n minus 1, at least when we have a bijective S-box. So in a bijective S-box, the first row and the first column are all zeros, except for the very first entry, which is 2 to the n minus 1. When we calculate LATs of bijective S-boxes, we see that the entries are all even, and we may wonder why that is. Let's just prove that it's true all the time. And this is a little bit of a technical part, but if you want to skip it, go ahead. But this is one way we can prove it. We have to assume that n is bigger than 1 for this to be true. One thing to notice is that since n is bigger than 1, 2 to the n minus 1 is even, right? And so the upper left corner having a value of 2 to the n minus 1, that's even. And since S is bijective, all the other values in the first row and first column are zeros, and those are even as well. Remember, 0 is even. So really what we have to prove is that the LAT have even integer entries when alpha and beta are non-zero. So let's take alpha and beta in F2n, and let's assume they're both non-zero. We're going to define 4 sets, A0, A1, B0, and B1. A0 and A1, these are really just a partition of F2n according to whether alpha dot x is 0 or 1. You know, when you do alpha dot x, where x is an arbitrary element of F2n, there's only 2 possible outcomes. It's either 0 or 1. And so we get, why don't we define those 2 subsets as A0 and A1? And that forms a partition, right? That means every element of F2n is in one of them, and A0 and A1, they have no elements in common. They are disjoint. And we do a similar thing for B0 and B1, except it's with beta dot S of x. That's either 0 or 1, and we define B0 and B1 accordingly. And that also forms a partition of F2n. So B0 and B1 are disjoint, and their union is all of F2n. Now we're going to use that lemma we just saw, remember? A0, by definition, that's why we worked on that lemma. We know the cardinality of A0 is 2 to the n minus 1. The set of all elements x, which have a dot product with the non-zero element alpha being 0, that has a cardinality of 2 to the n minus 1. And since it's a partition of f2n, which has cardinality 2 to the n, we know that a1 also has cardinality 2 to the n minus 1. So a0 and a1, they both have cardinality 2 to the n minus 1. And over on the b side here, S is a bijection. So by the lemma, b0 is also cardinality 2 to the n minus 1. S of x goes through all the elements of f2n since it's a bijection, so the lemma does apply. So b0 has cardinality 2 to the n minus 1, and therefore b1 also has cardinality 2 to the n minus 1, since it's a partition. And remember, since n is bigger than 1, 2 to the n minus 1 is even. So the main conclusion I just want to draw here is that all of these sets have an even cardinality. Now, to finish it off, why don't we define the cardinalities of these sets, AI intersection Bj, as Kij. If we look at A0, we can make a partition of A0 by intersecting A0 with B0 and B1. And since A0 has an even cardinality, that means this partition of A0, both of them have to be odd cardinality or both of them have to be even cardinality. This is an important point. So that would mean K00 is congruent to K01 mod 2. They have the same parity, right? We don't know if they're both even or they're both odd, but we do know they have the same parity. And then we can repeat this concept. For A1, we can partition A1 by intersecting it with B0 and B1. And since A1 has even cardinality, so K10 is congruent to K11 mod 2. And then we do the same thing for B0. We make a partition of B0 by intersecting with A0 and A1. And so those cardinalities have to be the same. Again, that's because the B0 has an even cardinality. If you partition a set of even cardinality into two subsets, both of those subsets have to have the same parity. Both are even or both are odd, right? And finally, we do the same thing with B1. We partition it with A0 B1 and A1 B1. And so the cardinalities of those sets are also congruent mod 2. So all four of those sets have the same parity mod 2. All of them are even or all of them are odd. Okay. Now we're ready to finish it off. One thing to notice is, you know, our solution of our main equation, alpha dot x plus beta dot s of x being 0, how can solutions of that come up? Well, either they're both summands are 0, so alpha dot x is 0, and beta dot s of x is 0. That's represented by A0 intersection B0. The other possibility is both summands are equal to 1, so alpha dot x is 1 and beta dot s of x is 1. That's represented by A1 intersection B1. So the set of solutions, which we've denoted sigma alpha beta, is just a union of A0 intersection B0 and A1 intersection B1. So the cardinality of sigma alpha beta, which we've written as E alpha beta, is K00 plus K11. And since those two are congruent mod 2, we know their sum is congruent to 0 mod 2. So that means it's an even integer, right? So we've proven that E alpha beta is even for every alpha and beta non-zero. And now we're done because remember the entry of the LAT, which is E prime, is just E minus 2 to the n minus 1. E alpha beta is even, we just proved that. 2 to the n minus 1 is even because n is bigger than 1. So we've just expressed the entry of the LAT, E prime, as the difference of two even integers. So it's even, and we're done. Yeah. So we've just proven that every entry of the LAT is even. Now, why don't we look at the complexity of this? We know that there's 2 to the n possible choices of alpha and 2 to the m possible choices of beta. So in total, there's 2 to the n times 2 to the m, which equals 2 to the n plus m possible equations to look at, right? And remember, we have to go through every element x in F2n. So we have 2 to the n plus m equations and 2 to the n possible solutions to look at, which gives us 2 to the power of 2n plus m. Now, usually n and m are going to be equal. So this is like 2 to the power of 3n. And very common values for S-box is 8 bits input and output. If we put 8 in there, we end up needing to look at 2 to the power of 24 calculations which is not a very large number, and that won't be any problem computationally. So let's finally get to writing some code to represent the LAT. And we're going to first need a dot product of 2-bit sequences. So we'll define a function called dot. It takes in 2 non-negative integers u and v. We imagine u and v as bit sequences. We start off by ANDing them, and then we need to add up all the bits of w now. So let's start off by just defining the dot to be 0, and then we'll run through the bits of w. So while w is not 0, we know that it has some non-trivial bits, and we'll access the lowest significant bit by doing w and 1, and then add it on to like a running sum, the dot. Adding will be through the XOR operator. And then we shift w over by 1 and to knock off the lowest significant bit, and then access the next lowest significant bit. Then we keep running through w until it's 0. And once w becomes 0, we know we've added up all the bits of w, and we return the dot. We can calculate the integer e alpha beta just by looping over x in f2n and counting the number of solutions to alpha.x plus beta.s of x being 0. And then once we know the value of e alpha beta, it's easy to get the lat entry e prime alpha beta. You just subtract 2 to the n minus 1, right? So we initialize e to be 0, and then as x ranges over 2 to the n, we check that if x is a solution to alpha.x plus beta.s of x being 0, if it is, we increment e by 1. And then after we've run through all the values of x, we've found the number of solutions e, and then we return the bias integer, which is e minus 2 to the n minus 1. So we can create a 2D array in Python with n rows and m columns, initialized all with zeros with this construction here. It's a little bit weird, but it works. And to code the lat, we just define a 2D array now with the number of rows being 2 to the power of n and the number of columns being 2 to the m. And then we're just going to populate it with the bias integers. So we initialize our table L, and then alpha and beta will range through 2 to the n and 2 to the m respectively. And then for each alpha and beta, we define the entry of the lat, L alpha beta, just to be the bias integer of the S-box for those particular alpha and betas. And then we return the lat. And it's as easy as that to calculate it. Now, in order to view this, of course, we would like to print it out. We could print it to the console real easily, just using this simple code here. And for a small table, it's fine. But when it gets a little bit larger, it's pretty awkward to look at it in the console. So we would like to maybe print it to a text file to study it better. And we can do that with this code. There's nothing interesting here. It's just adding some formatting. We're going to make it so there's column headers and row headers, and those will be in hex. The alpha and beta values are the headers, and they'll be in hex. But the entries of the lat will just be plain integers. So this code just prints the lat to a text file with a little bit of formatting. And we'll see how that looks in a little bit. A good little test for our code to see if this works is to look at the S-box in Haze tutorial. Haze has a really nice, well-known tutorial on cryptanalysis, given at the following link here. In this tutorial, he provides a little block cipher which he cracks using both linear cryptanalysis and then differential cryptanalysis. And it's just a twice cipher in the sense that it would never be used in a real-world situation, but it's good for learning. And this block cipher uses an S-box, given right here. We'll just denote it by H. It's just a small little 4-bit S-box. So it basically takes the numbers from 0 to 15 to the numbers from 0 to 15, the integers. And it's most conveniently just written in hex. So 0 to F needs to be bijectively mapped to 0 to F. And here's the definition of it. And we can write it in code like this, just using 0x to indicate to Python that it's a hex value. And on page 11, the linear approximation table is given. So our goal is to reproduce this table using our code. And we're going to see that our code will produce this table here. And that is the same as what was given on the previous slide. So just notice here that the number of bits here is 4. And 2 to the 4 minus 1, which is 2 to the 3, is 8. And that is the number in the upper left corner, right? We have 16 columns and 16 rows because it's 2 to the 4 is 16. Notice we have zeros in the first row and the first column, except for that 8, and we expect that. And notice all the entries are even as well, right? There's no odd entries here. So why don't we calculate the LAT of the Rijndael S-box as well? It's used in the AES block cipher. The Rijndael S-box is an 8-bit S-box, and here are the values of it. So if we just call our function on this value of r with 8 bits, input and output, we should get the LAT. It turns out to be this. Now this LAT is quite large because 2 to the 8 is 256. So this LAT has 256 rows and columns. Here's just a little piece of it. Notice the value in the upper left corner there is 128, which is 2 to the 8 minus 1, 2 to the 7. And we see that this LAT has some slightly large values, which are plus and minus 16. I think those are the most extreme values. We ignore the 128. We don't care about that one. We're looking for large values, plus or minus, that are not in the first column or first row. I think the value of plus or minus 16, even though it seems kind of large, is maybe not large enough to mount an attack by linear cryptanalysis, at least with the full number of rounds. All right, why don't we open a blank file now and try to code some of this up. Let's create a file called lat.py, and let's see how we can implement this. So just as in the video there, why don't we let capital S will be the S-box, and the way that'll be represented in code is just by a list of integers, usually given in hex. N is going to be the number of input bits, and M is the number of output bits. So for a bijective S-box, N is going to be equal to M. Alpha is the input mask, as in the video. Beta is the output mask. So alpha is N bits and beta is M bits. So we first have that dot product that we talked about. Just paste that there. And I won't go through the explanation again. Pretty clear. And then we have the function that calculates the bias integer. So this one, if we remember, it has, of course, the S-box, as well as the masks, and N is the number of input bits here. And we just run through every possible value of X, and we check if it satisfies our main equation there. If it does, we increment E by 1. Notice it's initialized at 0 at the beginning. And then after it exits this loop, the value of E is the number of solutions. And then the bias integer is E minus 2 to the n minus 1. So, and then to calculate the LAT is easy after we can calculate the bias integers, right? We just initialize a 2D array with zeros everywhere, and then run through all the possible values of alpha and beta. And then for each alpha and beta, we assign the value of the LAT at that particular location to be the bias integer. And that's it. And then we return the LAT. Now we can print the LAT to the screen. Why don't we just try that? That'll be with this code here. We can print it to the console. And why don't we put in Haze S-box there and see how that looks. So Haze S-box is given by this. And let's see how it looks if we print off the LAT. So H is a 4-bit S-box, remember, 4 input bits and 4 output bits. So let's see what happens when we run this here. And there it is. That's the LAT of Haze S-box. So that looks pretty good, but we could maybe do a little bit better just by printing it to a text file. So for that, we have our code there that we talked about a little bit. Why don't we insert that here? And that just makes some formatting. So we have some column headers and some row headers. We need to change our function now. We got to print the LAT to a file. So it's going to print it to a text file this time. When we run our file, it may seem like nothing happens, but in fact, a text file was created in our directory. Let's take a look at it. And here it is right here. So we notice that we have column and row headers now. And since this is a 4-bit S-box, they're going to go from 0 to 16 or 0 to 15, which is from 0 to F. All right. Notice we have our 2 to the 3 equals 8 in that corner. We have all zeros there and then all zeros there. We notice that we have a 6 is the largest number here. We have, looks like we have 1 positive 6 and 3 negative 6s there. So if we're trying to construct an attack with linear cryptanalysis, our eye is going to these particular values and the masks that are associated to them. Now, why don't we take a look at the Rijndael S-box and calculate its LAT. The values of it are given in this array, as we saw. Now this time we're going to go, we'll put R, and it'll be 8 bits to 8 bits. Let's see what happens this time. It actually takes some time. It doesn't happen instantly. I can hear my computer chugging along. I have an old processor, so it takes a long time. But it'll take a few seconds, but it's coming along. It'll eventually finish, I hope. All right, we're done. So now we'll take a look at it. And it looks pretty bad, but I have the word wrap on. So I'll shut that off. And there it is. So we have a table that's 256 rows and 256 columns, right? Notice it goes down to FF, which is 255. And we're going across as well. We can go across 0 to 255. So 256 rows and columns. We have all these zeros in the first row. Then we have all zeros in the first column, except for 2 to the power of 7 there. And notice everything's even. All the integers are even there. And I think the biggest number we see here is 16. And I think compared to the size, 256, 2 to the 8, it's not that bad. And I think in terms of linear cryptanalysis, this S-box is not showing a bad vulnerability, especially with the number of rounds. So this is the LAT of the Rijndael S-box. I just wanted to wrap the video up by just showing a couple small things. You know what? Remember in the case when n is equal to 1, we said that it's not true that the integers in the LAT are always even. Let's just verify that. Why don't we take our S-box to be just the identity S-box when we're dealing with the case n equals 1. And that's just mapping 0 to 0 and 1 to 1. This is not an interesting case at all, but just to show that we don't always get even integers in the S-box. Let's just verify that. See, there we got a 1. And if you do it the other way, there's really only 2 bijections from F2 to F2. This is one of them, and the other one is sending 0 to 1 and sending 1 to 0. Let's see what that LAT is. We have 1 and -1. Again, we don't have any, we don't have even integers there. Let's also just check out this little example. Let's take n to be 2 and m to be 3. And we'll consider a mapping of F22 to F23. It'll be 1 to 1. And really, we'll just make up any values here between 0 and 7. So let's try this. We'll do 1, 3, 5, 7. If we calculate the LAT of this S-box, we get even integers everywhere. Notice that we don't have all zeros in this top row because this is not bijection, this S-box. But if we play around, maybe just put a 4 here and then try the LAT, then now we have odd integers in there. So when the S-box is not a bijection, there could appear odd integers in the LAT. I just wanted to mention that small point. And that brings us to the end of this video. Thank you for watching.